Well, now that we looked at how the NMR functions and how to read some of the data, let's dig down a little bit deeper to really understand how this machine works on a more scientific/mathematical level. This is going to introduce some new vocab here, so let's make sure we get it all down. So what we've learned so far is that if you stick a nuclei in the NMR and turn it on and apply a magnetic field like this will have an affect on the nuclei and possibly make it go into the alpha spin state like this. Remember, this is the low energy parallel state of the nuclei. And we also saw that if we hook up some kind of light fixture here and we shine light which has energy at the nucleus like this, then the light gives the nucleus energy to go to the higher spin state, which is of course called the beta spin state. Now what we want to look at here is the amount of energy it takes to do that. Remember, different nuclei require different amounts of energy to bring them into this beta spin state. And there's a way to mathematically calculate that energy. It requires an equation you might have learned in physics or general chemistry. Look like this. Delta E, the change in energy, equals Planck's constant times the frequency of light. Remember, since h is a constant, then the change in energy only depends upon the frequency of light. Different frequencies of light, therefore, have different corresponding energies. However, when we apply this equation to the NMR, the frequency in this equation becomes the NMR operating frequency. Different NMRs operate at various frequencies. Various models are for sale. You can buy some as low as a frequency of 60 Hertz, or you can buy some hardcore ones like 950 megahertz. To connect this frequency variable in this equation to the actual NMR, we should look at another equation which looks like this. This equation says frequency is equal to gamma, which happens to be the gyromagnetic ratio of the nuclei that we're studying. So this doesn't have to do with the machine, it has to do with the actual nuclei. And we should just know that different nuclei have different gyromagnetic ratios. So underneath the gamma in the equation is the 2 pi, which is definitely a constant, and we're multiplying that by B. B is simply the magnetic field strength. It's the strength that the NMR machine applies. So if you plug in this second equation to the equation above, you get this overall equation for delta E. Some professors will put this equation on the exam simply because it's fair game, it's in your textbook, so you at least want to know where it came from and how to at least plug into it if you have to solve for something. And you'd also like to know things like this. For instance, notice, look at B right here, the magnetic field of the NMR. Notice it's proportional to the operating frequency. That means the higher the operating frequency, the higher the applied B field. Sometimes on an exam, we need to make connections like that. We're just knowing how variables are related. Let's look at another equation we can apply to what we've learned here. This equation involves a concept called effective magnetic field. The equation's very easy. This is what it looks like. B effective equals B applied minus B local. Let's make sure we know the variables before we plug into this. First of all, B applied, what is that? Well, that's this right here. That's the B field that the NMR applies. And what is this in red here, this B local? Well, that's the local magnetic field that surrounds the nuclei in the NMR. So B effective is simply the magnetic field that affects the nuclei, and what that's equal to is the applied magnetic field minus the local magnetic field. For our example proton that we have here, let's pretend we're going to calculate the B effective for that nuclei. Well, what we would do here is we would start with B effective, and we know what it's equal to, the B applied. And that, again, remember, is related to the NMR machine, whatever frequency it's operating at. But for our nuclei, notice there's no electrons around him. He is very de-shielded. Electrons are one of the things that affect your local magnetic environment, your B local. So since there's no electrons in the vicinity of this nuclei, we can say his B local is 0. That means that in this particular case, B effective must be a large number because we're taking the B applied and we're not subtracting anything from it. So we can say this de-shielded nucleus has a very high B effective. If this particular nuclei aligns itself with the magnetic field, And again, if we hook up our light machine here and we shine energy light at it like this, it will knock it up into the higher energy beta spin state. And because it just so happens that this nuclei has a very high B effective, that means it's going to take a lot of energy to get him into this beta spin state. Think about it. That nuclei had to make a 180-degree turn to go from alpha to beta. That's a long distance to travel. That's going to take a lot of energy to force him to do that. More so than a nuclei that doesn't have to do a full 180-degree turn. This is what's observed in the NMR for a very de-shielded nuclei. And the equation just proves the concept that if you're a very de-shielded nuclei, you have a higher energy to bring you into resonance or the beta spin state. These things are good to know, these technical details, just in case your exam goes a little bit more into the physics and the math behind what's happening here. Remember, we're aiming for mastery, and looking at the actual math and physics behind this is definitely going to lead to our mastery of the subject. We can never determine what our professor will put on an exam, so that's why we want to arm ourselves to the full. But let's also apply this concept to a very shielded nuclei. Notice what we have here. We have a nuclei in the NMR that has a lot of electrons around it. And again, let's try to calculate the B effective for this nuclei. Well, remember, it's the B applied, which is the same value as before. It's dependent on the NMR machine. And that means we turn on the machine, and this is what our B field lines would look like. Notice that diagram on the left there. Think of it as almost the electrons are absorbing some of that B field. Now let's turn our attention to B local. What is the B local for this nuclei? Well, if we look at the vicinity of that nuclei, we see that the electrons are included in it. And remember, electrons affect your B local. They increase it. So therefore, this case, the B local is not 0 like in the other nuclei. It's going to be some, let's say, high number. Who cares what it is? It's just non-zero. That means, again, we got to subtract it from the B applied. That means in this case, your B effective happens to be a smaller number now than before. So for this nuclei right here, which remember is considered shielded, the B effective is a lower value than a de-shielded proton. So what does that mean then? Well, that means that if we apply our light fixture here and we shine the energy light at the nuclei so that we could bring him into resonance, the beta spin state, this is what would happen in this case. Notice that nuclei didn't have to move that much to go into the beta higher energy state. So what that means to us then is this: if you have a lower B effective, it requires less energy to bring you into resonance. This is what's going on for a shielded proton, or any nuclei that we have in the NMR. And the connection we're trying to make here is that shielded protons simply require lower energy to bring them into resonance. Again, what we're showing here is the math to prove that truth. So what does this all mean? Let's break it down here. Let's put this over here like this. What we just saw is that if you're very shielded, that means you have a lower B effective. And remember, we're talking about the nuclei. It's the nuclei that has a lower B effective. That means that that nuclei requires, next arrow, lower energy. And lower energy for what? Lower energy to bring it into resonance. And that lower energy in turns to, on the NMR spectrum, a signal or peak that's upfield. These are the connections that I'd like you to make. And let's remind ourselves what we saw in the previous example. For that one, we had a very not shielded nuclei, or remember, de-shielded. And remember, because of that, he has a high B effective. And that high B effective means that it takes a higher, relatively, amount of energy to bring him into resonance. And that in turns corresponds to a signal or peak that will appear downfield in the NMR. Take some time to make sure you make these connections here. Like for instance, on an exam, if your professor shows a peak downfield and he simply asks you, well, what could be possibly true about that peak downfield? Well, look at the right-hand column here in the lower right, a downfield peak. Remember, going backwards in the arrow means what's true? It would take a lot of energy, a higher amount of energy to bring him into resonance. What's also true? That nuclei downfield has a higher B effective. And of course, we saw before what's true about that nuclei. He's very de-shielded. So we should be able to go both ways. And this is the concept right here that you see in front of you that I want to make sure you understand.